Hey chemists, in this lesson we're going to look at how we use percent compositions to find the formulas of a compound. Remember, one of the goals of people in chemistry is to sometimes have to identify what a substance is. You know, they never look like the picture. There's a picture of what's called the carvone molecule, and carvone is a white, waxy solid. It doesn't look like this or even its constituent elements, but we have ways of analytically determining what the formula of something is. And one of them is to use what are called percent compositions. So first we're going to introduce what a percent composition is, and then we'll see how we turn it into an empirical formula. A percent composition is the percentage of an element in the compound. So if I wanted to look at, let's say, the percent carbon in this ethanol molecule, that would be the grams of carbon divided by the grams of the whole thing, C2H5OH, and then you multiply by 100. Now, it's easy to just assume some arbitrary amount, and I'm going to pretend we have 1 mole of this substance, because then how much carbon is in this? Well, it'd be 2 moles of carbon, which is 2 times 12. And then the denominator becomes the molar mass of that compound. So the molar mass, remember, is the sum of all the atomic masses, 2 times 12 for the carbon, plus 6 for the hydrogens, plus 16 for the oxygens, and when you add that up, you get 46 grams per mole. So if I assume we're talking about 1 mole of substance, this becomes 46 in my denominator, and then I multiply by 100, and I'm going to round that to the nearest whole percentage. I get 52% carbon. How much you round these two is a little bit arbitrary because it depends on how precise your atomic masses are, which really just depends on what periodic table you're looking at. So you might see a variety of precisions given, but give something within reason based on the numbers that you're using. So I'd like you to hit pause and try these other two. What's the percent of hydrogen in carvone and nitrogen in penicillin? Try that now. Okay, for 17 we want the percent H. And to do that I need the molar masses of these. Well, 10 times 12 each for the carbons, plus 14 for the hydrogens, and 16 for the oxygen is 150. So I want H, that's going to be the 14 for the H's, divided by 150, multiply by 100, I get a little bit more than 9%. Hydrogen. Penicillin is a much bigger molecule. I've got 14 times 12 for each carbon, 20 for the hydrogens, 2 times 14 for each nitrogen, 32 for the sulfur, and 4 times 16 for those oxygens. That gives me 312 grams per mole. So my percent nitrogen would be the nitrogens, 2 times 14, divided by the total, 312, multiply it by 100, and I'll go to 2 sig figs here as well. I get 9% nitrogen. So that's just what they mean, but most of the time we're not going to be calculating percent by masses. We're going to be given percent by masses and have to turn them into a formula. So let's talk about how we do that, because we have ways of experimentally getting mass percentages, and then we can turn those into formulas. This is called finding the empirical, which means the simplest formula of a compound. And to do this, there are 3 steps. I'm going to write them up here. Step 1, we need to assume an arbitrary amount of the substance, and I highly recommend 100 grams. That way, step 2, you can take your percentages and just call them gram values, and then you can convert them to moles. And then step 3, we simply normalize the ratio. I'll explain what that means when we actually do it in a problem. So let's take a look at one right now. Given these percentages of carbon, hydrogen, and chlorine, and a molar mass of the compound, what's the formula of that compound? Well, I'm going to rewrite those percentages of each one. We have 24.27% carbon, and we have 4.07% hydrogen, and then the difference from that and 100 would be the 71.65%, and that's chlorine. Now, if I assume 100 grams, those percentages actually become gram values. because if it's 100 grams and those are percentages, these have to add up to 100. Now I have to convert each of these into moles. So I'll do the hydrogen. There's 1 mole of H per 1 gram of H. So I get 4.07 moles of H. You can hit pause and do the carbon up there and the chlorine down there. Okay, let's see how you did. In 1 mole of carbon, there's 12 grams of carbon. In 1 mole of chlorine, there's 35.45 grams of chlorine. Remember, those are the numbers just from our periodic table. So my carbon becomes 2.023 moles of carbon, and my chlorine becomes 2.021 moles of chlorine. Interesting, they're very close to each other. Speaking of sig figs, I know I just mentioned earlier we can be arbitrary when we're doing the original percentages, but here, once we're given them, I would highly recommend, if you're given very precise sig figs for the percentages, carry those as you do your calculations in the beginning. It makes it much easier to see what the nearest whole number ratio is going to be. So 4 sig figs in the carbon percentage, I have 4 sig figs in the moles of carbon. 3 in the hydrogen, 3 in the hydrogen, etc. So that takes care of step 1 and step 2. Now we need to do step 3, which is just normalize this. And here's what these mole values mean. They're a ratio of how many of each element you have. And I'm going to write them as if they're subscripts. The ratio of carbon is 2.023 to hydrogen, 4.07 to chlorine, 2.021. Now, I know, first of all, it looks bizarre because there's decimals. We never have decimals for compounds like this. And you might say, well, you know what, those are actually pretty close to whole numbers, and we might be done. And you're right, that could be the case, but the proper way to normalize is to take those mole values and divide by whatever your smallest one is, which in this case happens to be the chlorine. 2.021, 2.021, and 2.021. This is called normalizing to get a, hopefully, close to whole number ratio. And indeed we do. We get a ratio of C roughly 1, H roughly 2, and Cl exactly 1. That's called your empirical formula. And that's all you can actually get from the percentages. However, they gave us one more thing. They gave us the molar mass. The molar mass is just under 99. So we can actually get what's called an empirical mass and compare it. The empirical mass is simply the weight of the empirical formula. So that would be the carbon, 12, plus 2 for the hydrogen, plus 35.45 for the chlorine, and I get 49.45. And then I look at that and I compare that with the molar mass. And if it's the same, we're done. But it's not the same. So I have to ask myself, how much do I scale that up to get to the molar mass? And if you can't see it, you can actually take the molar mass, which is given as 98.96, and divide by the empirical mass, 49.45, and you get almost exactly 2. So our formula, our molecular formula, is in fact C2H4Cl2, which, as a coincidence, is exactly what it looked like in the beginning, but that's rare. That really just came up as a coincidence here. That's called the molecular formula. The empirical formula is just the lowest whole number ratio, 1 to 2 to 1. The molecular formula tells you what this compound actually looks like. We actually still don't know the structure. If you want to think about this just for a second, go back to our first unit and imagine how could you connect some carbons, 4 hydrogens, and 2 chlorines. Well, I've got, the possibility of the 2 carbons connected to each other and 1 chlorine on each. That's called 1,2-dichloroethane. Or I could have the 2 chlorines on the same carbon, and then the rest of the hydrogens are distributed throughout, That's called 1,1-dichlorine. So we still don't actually know the structure. I would need something like a proton NMR to get what the actual structure is. But we certainly have narrowed down what this compound looks like thanks to those mass percentages, turning it into a formula. Okay, so let's try one more together. We've got phosphorus and oxygen and a molar mass. So I'm going to take those percentages and just rewrite them. We have 43.64. I'm going to turn it into a gram of phosphorus. We have 56.36% of oxygen, so I'm going to make that a gram of oxygen. To turn these into moles, you divide by the atomic mass. Phosphorus is 31. Oxygen is 16. So I get 1.408 moles of phosphorus. I get 3.523 moles of oxygen, and now we normalize. I like to do this by just writing a fake formula first, so P, 1.408, O, 3.523, and then divide each one by the smaller one, that's the phosphorus value. And this one actually gives me 1 phosphorus, and if you look at your calculator, you get almost exactly 2.5 oxygens, so you actually have to normalize again. And here you just use some common sense. Multiply by 2, you get an empirical formula of P2O5. Now P2O5, if you add up 2 times 31 plus 5 times 16, I get an empirical mass of 142. And then I look at that and I compare that with essentially 284, and once again we have to multiply our subscripts by 2. So the molecular formula, when all is said and done, I'm not even going to write that out, I'm just going to say the molecular formula, it's not P2O5, but P4O10. So I want you to hit pause once more and see if you can do the last one. There's a compound this time with 4 elements and a given molar mass. Go through the same steps we just did and see if you can get the correct formula for that. Okay, let's see how we did. So we have 49.48 grams of carbon times 1/12. I got 4.123. That's my moles of carbon. The hydrogen, that's the easy one, 5.15 times 1/1, so 5.15 moles of H. Then we have nitrogen, 28.87 times 1/14. It gives me 2.062 moles of N. Notice I'm using the monoatomic mass for each of these elements. We're not talking diatomics. I want moles of N, not moles of N2. Likewise, carbon, 16.49 times 1/16. I get a little more than 1.031. And I am carrying my sig figs. You get much better results if you don't round along the way, or at least carry how many sig figs you have. So when I normalize, I have carbon, 4.123, hydrogen, 5.15, nitrogen, 2.062, and oxygen, 1.031. We normalize, divide all of them by the smallest one, that's the oxygen value. So everybody gets divided by 1.031. That turns into roughly C4, H5, and 2O. You add up all those masses, you get 97 grams per mole, and this is just a coincidence, but yes, every single time it's been exactly half. So our correct molar mass is going to be C8, H10, and 4O2. That's how many of each element are in that molecule. So that's an introduction to percent composition, and then more importantly, how we take those percentages and turn them into molecular formulas.